that force that we found is going to be active.
There's an example of one.
80 minus
So that's joint A. So we got sum of Fy is 0.
This is its own force. And this is its own force. This is its own force.
So 10,000 up, and then minus sine 26.6 down times FAC.
As we take this snapshot right here.
Solve for FAC, you get that.
This is just
And sum of FX is 0. Minus cosine 26.6 times 22,361 plus FAB.
Where do we have it?
Okay.
Where's the only
FAB is 20,000.
that we have a number?
Okay.
Which is up in the y direction. So let's set all our forces for y equal to 0 first, because we have an actual. So you're given 16,000.
So do we, so here's the run through on joint A.
But then you start adding this in.
So if you have questions, let me know here. What I'm doing there, I'm going sum of Fy, I'm setting it equal to 0.
Really? Yeah. I think that's kind of what I was thinking.
Kind of starting to go through it.
Okay, so sum of Fy is 0. I got 10,000 up, like that. And as I have it drawn, I got FAC down. But I want the component of it that goes down. So I'm going to do the opposite side. So that'll be the sine, because it's the opposite side. So what that is there is sine 26.6 times FAC. And it's down, so it's negative. When I solve for FAC, I get a positive answer. That means my assumption was correct. It does act down and to the left, so it does push. So that means it's compression. Do we have any questions on that? All right. So that is compression, because I assumed it was down left. I got a positive answer, and so that is means it is compression.
So it's based on our assumption of where the force is acting that we say it's like compression.
Right. Yeah. The way this worked was I assumed it was down. That's where that negative sign came from. My answer came out positive. That means it does act down.
And if it came out negative, then that means you're wrong. It's coming out the other.
Right. Correct. And it is pushing on the joint, so it's compression. Okay. Then I go sum of Fx. So we good with that? Okay. Sum of Fx is 0. I get minus cosine 26.6. I'm doing cosine because I'm doing the adjacent side to the angle. That one is negative because it's going to the left. And I got what the answer I just got, 22,361. And then I show FAB going to the right, so that's a positive. Solve for FAB, it's 20,000. Pulling to the right. That's pulling on the joint to the right, going that way. It's tension. Okay. Now, as I'm going through this, I can kind of put these arrows in here. Remember, they always act in an opposite way. This is 22,361, and the other one is 20,000. Like that. So that kind of tells me where I could go next. I could go to joint B next. That might be the easiest place to go. You could go to joint C also, but I think B would be easier. Okay, we're good? It's 20,000 there. Okay. So I go to joint B. I got the 16,000 down. I got sine of that angle, which is 63.4 up. So FBC is 17,889 up. It's pulling up, so it's tension. Doing that. And then I put everything into sum of FX. I got the tension in AB, which is 20,000. to the left. I got BD to the right, and I've got cosine of the angle times 17,889, positive. Okay, so for BD, it's 12,000. Okay. So we good with this? We got any questions on this stuff? Okay.
Yeah.
That's the basics on that, okay? So I have the answers up on the board. This is just kind of practice on this. It looks like I had a bit of a typo in Moodle. I'd like you to do 292, which is actually on page 17B, and 294, which is on page 17C, and also 281, which we'll get to here. And those are due on Wednesday, okay? So AB is 20,000 tension. AC is 22,361 compression. BC is 17,889. Tension. And there's 12,000 tension. And that's 13,417 compression for the last one. So there's the answers, okay? We good with that? Okay. All right. Now we've got this other one that gets a little bit tricky because you get into a joint that's a little bit tricky on 294. So let's see how to handle that. And let's look at, I think it's 505 out of your packet. This is an example of how to do that. Because sometimes you get into problems that are where you get angled members, and that can cause a little bit of difficulty. So I'm on 505. Got this, what we call a cantilever truss. So that's just a truss like on an awning or something sticking out from a building. You know, so what I'm doing there is I'm doing the trigonometry on the joints. And then I'm finding the reactions. So this is supporting loads that you're seeing there. These two loads. Like so and like so. What they're going to tend to do is take that truss and try and rotate it clockwise. So what's going to happen down here is that reaction is going to come to the right to counteract that, see? Now, if the lower reaction is to the right and we don't have any applied X forces, the upper reaction is to the left. Okay? And then you've got a Y reaction going up to counter those other reactions going down. That's kind of what's happening there. And I've got the trigonometry on the angles. Now, I just want to illustrate something you can run into. And this will be something that might come up on your homework just a little bit, so I wanted to point it out. And what that is when you get into these joints that have two angled members coming into them, there's two things you can run into with that, okay? So why don't we look at joint E here? Let's just go right to joint E. You can't solve that because there's a known force and only two unknowns, CE and DE. I did the trig there, and they're both on 10.6 degrees for the angles of CE and DE. Okay? So that's what I've got going on. So I'm going to have a look at joint D, or excuse me, joint E. That's what I'm going to do. Okay? Now there's two ways I can solve that. So for my joint E here, what I've got is I've got two forces coming in. Now, you kind of common sense this stuff out a little bit, or I don't know, I guess you develop common sense. I guess it's not that common all the time, but if this force is pushing down on E, it's going to kind of push in on DE. So my guess is that DE is going to push back as that force comes down, and that's 12,000. Okay? So if DE pushes back in the direction shown, CE is going to come back the other direction. So CE is kind of getting pulled in tension. DE is getting pushed on. It's in compression. So that's probably a pretty good guess at how those act. I didn't draw the angles quite right, but there's a free body diagram for that joint, okay? Like so. Now, when you have that, there's two ways you can solve it. You know, you can use the standard XY axes, and if you do that, you're going to have two equations and two unknowns is what you're going to end up with, because there isn't like one force. You can't get one unknown in a particular direction there. Okay. So if I go ahead and do that, I'd go sum of fx. What I'm doing here, I'm using a standard axis system. Would be cosine 10 FDE minus cosine 10 FCE. And when I work through that, I'll find that FDE and FCE equal each other because the joint's balanced in the x direction. So what I'm going to have to do here is get two equations and two unknowns. When I have sum of Fy, set that equal to 0, I get sine 10 FDE plus sine 10.6 FDE plus sine 10.6 FCE minus 12,000 is 0. So there's two equations, two unknowns. I just have to solve them simultaneously. So I just went through a simultaneous equation solution there. If you have a solver on your calculator, you can just plug them in on the homework. You could put them into a matrix too if you wanted, okay? So I get FDE is equal to FCE, and then I can work through my sum of Fy equation. Sine of 10.6 FDE plus sine 10.6 FCE minus 12,000 is 0. And then I can plug in FCE in for FDE. So I'll get 0.184 FDE plus 0.184 FCE is 12,000, but FCE and FDE are the same, so that's 0.184 FCE plus 0.184 FCE is 12,000. Can sum these two together and get the total FCE as 0.368. So FCE comes out to be 32,617, as does FDE because they're equal. Okay, so that's one way to go through it. Two equations with two unknowns. Now this one worked out pretty well because the angles were equal to each other. But if they're not, you can still solve these out. You know, if they're not, the equation gets a little bit more involved. So there is another way to solve one of these, and it's to use those inclined axes that I was showing you a while back. Okay. So if you go with inclined axes, what I would do, I would set up an axis system like this. X prime and Y prime. Now when you do this, a lot of times your algebra gets a little bit simpler, but the price you pay for that is your geometry gets a little bit more complicated. So you have to be able to deal with the geometry. I think that's 21.2 degrees there. Okay, I can extend that out like so. What do we got? We've got a vertical line here. So if I kind of make that a vertical line and say that's 180 degrees total, I can take away this angle right here, which is 10.6. And what else? And take away this 90. And that will get me that remainder angle that will go up here. Okay. So I could go ahead and do that. So I get 79.4 degrees for that angle up here. So if you want to go through that bit with the geometry, you can use these inclined axes and solve it out with one equation and one unknown each time. That's all really I wanted to point out, is if you get into this situation where you've got two angled members coming into a joint, you can either use two equations and two unknowns, or you can use inclined axes. So if I do it this way, I get sum of Fy prime as sine 21.2, that's this one, times FCE minus sine 79.4, that's that one, times 12,000. So FCE is 32,556. Pulling, so it's tension. And then I go sum of fx prime and get FDE minus cosine 21.2, 32,556. And then minus cosine 74 times 12,000. And that would get me FDE, okay? So you can do it that way, if you like. Either way. Because on 294, there is a joint that's a little bit tricky. It's got a couple angled members in it, okay? So are we all right with that approach? So you can either go two equations to unknowns or use inclined axes. Okay. All right, now let's go look at 281. That's also assigned if we're good with that. Okay. So 281 is a 3D problem. Probably my approach on this would probably be a visual kind of approach on this one. So there you go, here's 281. Now what I want to do, if I'm going to use a visual approach, is kind of figure out equations I can use where I take moments about axes to solve for a force, okay, individually. So on this one, what I've got is I've got three unknowns, okay? And then I've got one force down. And the force down is 6,000 newtons. And then I have the three forces up. Like so, okay? So there's a quick free body diagram of the thing. So this is 281. All right, now if I want to do this visually, what I want to do is find a moment equation I can generate that'll have just one unknown associated with it when I do the moments. I've got a little typo there. That should be FCF. There we go. Okay. So I want to kind of look at that and go, okay, which way am I going to, where would I want to take a moment about to find that unknown? So I want to find an axis that I can take a moment about that'll only have one unknown. I bet if I look down that axis right there, that might fit the bill, because if I do that, that's the x-axis. And what I have acting there are two unknowns right on the axis. And I've only got three unknowns, so if I take that moment about the x-axis, I'll only have one unknown left. Okay, and I'll have the 6,000 down there, 2 meter distance, and then I'll have FCF acting that way. Okay, and I can sum moments about x, set that equal to 0, and I bet when I'll do that I'll come up with FCF. And that'll be 3,000 newtons, I think. We doing all right with that? So I'm going to look down the x-axis. Okay. All right, so that gets me FCF. It would now be 3,000. Now once I have that, that's a known. So this is 3,000 newtons. Now I ought to be able to come up with another moment equation I could use to solve for one of the other unknowns. Okay. So to finish this thing up, I think what I would do would be to do another moment equation. Yeah, sure thing.
Is that FAB or is that FAB?
Where?
Up top.
I'm
sorry, about your x moment when you project looking down the x-axis.
Mm-hmm. What I've
FB,
that's a B.
Okay.
So it's, oh, that is a D, and then, okay, thank you. Got a typo. That'd be FAD. There we go. Thanks. Okay.
Is it 3,000 newtons just because it's half the distance of?
It's 3,000 newtons because, the calculations come out that way. Does have a lot to do with the fact that 6,000 is halfway from between the x-axis and FCF. Yeah. But when you run a moment equation, it'll come out that way too. There is always kind of the intuition on this, but then the calculations back that up. Okay. I'd probably take another moment equation and get FBE, and that would be 2,000. And then to finish it up, I'd go sum of FC equals 0, and get the last one, and that would get me FAD. Okay. So that's the approach I would take on that. Take the 3D problem and turn it into a series of 2D problems. There's your basic free body diagram to start. So we got any questions on that one? Okay. Now you could also do a full-blown vector approach on this if you like, and that would work as well. So, whichever ways work for you are fine. So, just use whatever methods are most effective for you. Okay, we good on that? So if you're going to do a vector approach, you're just going to sum up the vectors. There's 3 of them to sum up. So what you would have on this would be, for the first one, we're going to take a moment about A. That's where the origin is. That makes the moment arms easier to figure out. We're going to have FB right here. That has a moment arm of just 3 in the X. So that's why the R is 3, 0, 0. And then the force is 0, 0, FB. Okay. From there, you can go ahead and find the moment of FC. Okay, to get there, you would go over 4 and up 1, I think. So it's 1 in the X, 4 in the Y. So the moment arm on that would be 140. And then you'd have 0, 0, FC. And then the last moment equation that you would need would be right there, and that's for 6,000 newtons, like so. And you'd have to figure out, a force expression for that and a moment arm for that. So you want to get from the origin to the center of gravity for the moment arm, and just write up an expression for the force there. It's a K vector, I think. So we good with that? Question?
Yeah.
So
I'll think about it. I'm just confused on where the other moment is.
the other moment?
Yeah, in terms of, because you said it's in the x-axis, but if it's free-hanging, I'm just confused.
The other, like the first
sum of
method?
moments, I'm sorry.
So,
Yeah,
oh, this one?
from the beginning.
Oh, like back this way?
Yeah,
Okay.
but you left it there.
Yeah, I did. Kind of, I mean, this might sound kind of funny, but, I've done this in my office before. I build models and stuff because it helps me see stuff. Anything I can do to see stuff. Get a book and put 3 pens going up on it. Just turn the book and look down. What axis can you look down such that you only got one unknown force acting on it? Okay. Tissue box. Where's the tissue box?
On the table.
Right there.
All right. All right. What are my odds of success at actually pointing this on without dropping it? I don't think they're very good.
3-1. Almost that.
My odds aren't good. Anyway, I don't think I'm gonna pull that off. Wasn't meant to be there. Okay, so, no, it's like this. Can you see how I'm looking down here? And that's off to my right, the force?
Yeah.
How about if I come over here? What happens if I come over here? And look down this way, what am I gonna see? I have to get way in the corner here. If I do that, what's going on? What
You're
am I
gonna see 3 upward.
I'm gonna see what? I'm gonna be looking right down the y-axis, right?
Yeah.
I'm looking down the y-axis, what am I gonna see?
Oh, you're just gonna see the 1.
Off to the left, I'm gonna see forces, right? You kind of do that in your mind.
Oh, okay.
Okay.
From this way. So you're gonna see 3. You're gonna see 3.
You're gonna be looking right down there, you're gonna see that up, down, but you know this one, you know that one. There's only one you don't know.
So because FAD is on the y-axis when you're looking at it?
Yeah. If it's on the axis, it causes no moment.
It causes nothing. Okay.
Good?
Other questions on that? We good? All right. All right, let's look at one other aspect of trusses here then. So that stuff's due Wednesday. So there's 281, 292, 294. I had a little bit of a typo in Moodle, but I fixed it up. So 292 is on page 17B, 294 is on page 17C. List your answers in the order that they're shown on pages 17B and C. Okay. Okay, let's have a look at finding these, what we're calling zero force numbers. What I'd like to do is to get you to a place where you can do this visually. So let's look at 510. So we found a couple of these already, these zero force members. They're forces that are members that carry no load. Okay, you identify them with method of joints. If you can find a joint for which either the equation is sum of fx or sum of y equals 0 has only one member and no applied forces, it's going to zero out that one member. Okay? So we use a method of joints approach to find these. You can find it at one joint or the other. And if you can prove at a given joint that a member is 0, it's 0. Okay? It may be apparent only at one joint and not on the other. We've already found a couple of these. Let's see what else we can do with this to find. Let's get kind of systematic at finding these. So let's go over here to this joint right here, joint A. Now I'm on page 510. If I go sum of fx and set it equal to 0, what is that going to equal? It will equal FAC, right? So what that means is FAC is a zero force member. It doesn't carry any force, because if there's any force in AC, it'll create an unbalanced joint at A in the x direction, and A will start to accelerate, which it isn't doing. It's in static equilibrium. So based on that, FAC is what we call a zero force member. When I find them, I put zeros on them. That's carrying no load. Okay? We good with that? Now, I cannot see that at joint C. It is not at all apparent to me at joint C that AC is 0. However, it is quite apparent at joint A. So if I find it at A, it's 0. I don't need to get caught up in looking at C at all. All I got to do is prove it's 0 at one joint. That's all I got to do. So you see any other zero forces in there?
DF?
DF.
Or, no.
Yeah, don't. Yeah, now joint F has three unknowns. It's just too much to really sort out. And joint D, I couldn't tell much about DF there. I think there's two more in this truss.
Is it PD?
CD, yeah. Why is this 0? Where do you prove it to yourself?
Because the load is going to be from BC and CF,
It will.
and there's no, I don't know how to word it.
It's at an equilibrium, right? Because all the forces, they're all distributed equally on each side of every. Right?
Okay, I think you're kind of on the intuition side of it. The kind of the proof of it to me is right here. If I look at joint D and I set that equal to 0, the sum of forces there, and I look at the y direction, that will just 0 out. Okay, and what I'm going to have is CD is 0 if I look in the y direction for that joint. Are we good with that?
So because C has all the other like member forces meeting at a single point, you don't have to think about them.
It's got nothing to do with C. You have to just focus on it. You just look at D. If you can prove it's 0 at D, it's 0, regardless of what's happening at C. There's just too much going on at C for me to make much of a conclusion there.
So it's from B to F. When you're looking at D, you still have the two.
Yeah, and they're probably equal and opposite. I can't draw many conclusions about BD and DF because I just don't have a place to get in there and start looking at them.
Okay.
Those two corners both have three unknowns, which is too much to really do. I bet BD and DF are equal and opposite, but that's really about all I can say about it. Okay. And I can look at joint D, and I can get the fact that it's sum of Fy is 0 there, so CD is 0. Now I have some computer problems here again, so I'm going to just save this. So I've got something.